So we have started the course. We were talking about introduced groups, subgroups, and we talked introduced concepts for a group, the order of the group, and we finished with Lagrange's theorem. Which says that if G is a finite group, and H subgroup, then the order H divides the order G. Here we want to give a few simple consequences of this, a few corollaries. First, I call the order of an element just the smallest power, so that we have 1. So this group A in G, and the order of G, the order of A of C is the smallest integer with equals again 1 if such an element exists. Otherwise, it's zero. Okay, so this is the order. So, for instance, the order of the neutral element is 1, and in Z, in addition, the order of every element which is not the zero element is infinity. So, in this case, the neutral element is 0, and we want to get 0. Okay. So, corollary. So, G is a finite group. And A is an element in G. Then it follows the order of A divides G. The order of G. Some sentences here. It's easy to see. We'll see now that the order of the subgroup, the second subgroup generated by A, is just the same as the order of A, and so therefore it follows. So definition of proof that A is subgroup generated by A, and show that the order of the subgroup is equal to the order of A. And then obviously this is a subgroup, and so therefore its order divides over T. In fact, again, we can say precisely what the elements are. We have that A is equal to the set consisting of 1 A to the order of A minus 1, and all these elements are different. And that would take it. So first, that this A is contained, I mean, is equal to the set. So that by definition, A is equal to the set of all A to the n, in the set. So then we make the division of the rest. By the order of A, we can write any integer n as d times the order of A plus the rest, where d is an integer, and r lies in 0 and the order of A minus 1. So then A to the n is equal to A to the order of A plus r, which is A to the order of A to the p times A to the r. This one is 1, so this is A to the r. And so we see that every element subgroup is of this form, and then we want to see, we have to also see that they are all different. Okay, so on the other hand, if A to the R1 is equal to A to the R2, here smaller than equal to R1 smaller than R2, smaller than or A minus 1, then we have that so this is equal, so therefore A to the R2 minus R1. Yes.
I think that it's a little under A minus 1.
What?
Like that last inequality. Are also
Yeah, right. That's misprint. Thank you. Okay, so this is therefore this divided by this, so this is 1, and we have that 0 smaller equals to R3. So it's strictly smaller now than it was. Okay. And so this is so we find the power. This. This is strict inequality because they're different, and so we find the smaller power, which is already 1, and this constitutes of the order of A. So therefore, so this is very simple. Maybe I should have done all this detail, but okay. Another corollary of this is that again G is a finite group. A and G, and then it follows that in A to the order of G is 1. And this is just because the order of G equals to order of A times some number D, which is actually the index of the subgroup in E. in G, and so it follows A in A, so the order of A is equal to 1 to it. So this is also simple. Another final corollary also here is that if the order of the group is a prime number, then the group is cyclic, so it's generated by one element. So that is cool. And with the prime number, and then G is cyclic. So the divisors of the order of G are just 1 and the order of G. So if I take any element in G which is not the unit element, which is not the 1, then the subgroup generated by it the cyclic subgroup generated by it is a subgroup which is not just 1, and so it must be the whole of G. And so the group is generated by any element which is not the neutral element. Okay. Okay, so that was as much as I wanted for a moment to say about these simple consequences of Lagrange theorem. Are there any questions? So otherwise, I now want to start talking about normal subgroups. Both groups. So we know what a subgroup is. There are some subgroups which are nicer than others. And the point is, maybe really the motivation for this is the following. So let here's this group, and H is subgroup. So then we can look at the set of cosets, so the quotient set. So we can ask ourselves, can we make G mod H into a group? But there might be some crazy way of doing it, but there's an obvious way how we would like to do it. So in the obvious way, namely by putting setting A times H times P times H. The obvious way how we want to define a group structure on this quotient set, on the set of cosets, and is it a group? It turns out that it sometimes is and it sometimes isn't. And the condition for this to be a group is that this group is a normal subgroup. So let's look at the condition. So what we need is that this product is well defined. So that means it does not depend on the representatives A and E that we take. So that means if A H is equal to prime H is equal to prime H. Is it true? That we have ADH is equal to P prime. Let's look just at a very simple case. For instance, we can take as an example for this A just to be one in the group, B prime, an element H in H, so from element H to H, and which we kind of choose general, and B and B prime we take equal, and this is just some element in G. So we can look at this particular case. So then the condition here is that then we want for this to hold, then the statement then becomes that BH in B times small h. No, BH is equal to H. Right? Yes. Okay. So now we can multiply here by b to the minus 1. So this is equivalent. So h is equal to b to the minus 1 h. And this is equivalent to know that multiplying by an element to stay in H is equivalent to saying that this element was in H. So this is equivalent to saying that e to the minus 1 H is in H. So this H here was general, this E was general. So it's a necessary condition for this product to be well defined is that for every element B in G and every H in H, BH, or B to the minus 1 H is in H, or one usually writes the other way around, BH B to the minus 1 is in H. And this is our definition for normal subgroup within the condition is also sufficient. Definition. So the subgroup H in G is called normal subgroup group if say differently G H G to the minus 1 H for all elements G and G or H and H. Okay, so this is so just some quick examples. Again, and all subgroups are normal subgroups. Because then, if I take G H G to the minus 1, this is equal to G G to the minus 1 times H, so this is equal to H. And H was an H, so G. Okay, so there's nothing there. And then it's also clear from the definition that 1 and G itself are normal subgroups. Of any G. So the full group of just the new group consisting of the two elements. normal subgroups directly from the definition. Let's look at one example. So we look at S3. Group of 3 letters in S3. I claim that if I look at the group H, we can say 1, 2, 3, 1, 2, 3, so the identity element, and say 1, 2, 3, 1, 2. This group is not normal. Then I think it was an exercise to check that. And on the other hand, if you take here maybe G, which is the group consisting of again the neutral element, and somehow the cyclic permutations they always go from more. 1, 2, 3, 2, 1, 1, 2, 3, 3, 1, 2. This is the normal set. Okay. You can do the computation. In that case, if you write, if you write, write down. For this particular one here, if I write this thing 1, 2, 3, 2, 3, and this thing here 1, 2, 3, 1, 2, 2, 1, 2, 3, 2, 1, 3. You can see that this element 1, 2, 3, 2, 1, 3, if I apply twice, it's the identity, so this is its own inverse, so this is actually conjugation, and this will be equal to 1, 2, 1. And so it shows that this element, if I conjugate like this, doesn't lie in H, so it's not normal. Okay. That. And now the way I motivate this definition is that now we would get a group by defining this, so we had better actually get a group. So this is called whatever, sometimes smart, but I call it definition. So G group H of the subgroup then if I take set of process with H with the object product for A times H, so AH times PH is AH. Or vector group or vector group or function group or there's not much to show. Basically, if we do this computation inside more carefully, you see the multiplication is well defined. So the product is well defined. So we take some elements A prime, B prime, and B with the AH, A prime H, BH, then, so what does it mean? It means, so what does it mean? It means that if I take A prime, this can be obtained by from A to multiply an element by an element in H. So from A times H1 prime, the relation is T times H2 with H1 and H2 elements in H. And so if I now take A prime, B prime, this is called H1, H2. But now at some point I want to use this property negation, so I can just put e to the minus 1 somewhere in between. So I write this as AB, e to the minus 1. H1, B, H2. And I can factor it like this. So here we see we have b to the minus 1, H1B. So this is an element in H. And so we have here, therefore, A prime B prime is AB times product of two elements in H. So it means that A prime B prime times H is equal to AB times H. So the product is well defined. And the rest of the group actions somehow obvious from the definition, you can check it directly. So associativity follows from the associativity of the group. And so group actions are obvious. And when I don't use the associativity, but for instance, we have a neutral element is 1 times H, and the inverse of AH minus 1. That's by definition. This is just the way I define the product. Okay. Okay, so this was what I for the moment wanted to say about this quotient groups, or vector groups. So we see that they are also connected to homomorphisms, which become now true. So group homomorphisms. So this is somehow the standard thinking all the arms of mathematics. If you study some structure, like a group, a vector space, whatever, manifold, groups, vector space, manifolds, you are interested in match between these things which are compatible with the structure. So for manifolds, it would be differential maps, for instance. For vector space, it would be linear maps. And so here for a group, the only structure that we really have is the product. So the group homomorphism should be mapped from one group to the other, which sends the product of two elements to the product of the image. And so, see? So definition. map F from G to H is called the group homomorphism. For the moment, let us say homomorphism or homomorphism. If, well, let us say it's compatible with the product. So if I take it, apply F to the product AG in G, this is F A times F of G for all the so the sense product of any two elements to the corresponding product of the image. So that's homomorphism, and well, usually in any field, in most fields, the homomorphisms are the main tool to study the objects that you want to study. Okay, so for instance, we have so the multiplication k times k from z to z sends number n. So k times n is a homomorphism of z to itself. Z multiplication. So, another one which will be special we'll see later also can look at the projection, say from Z, so what we call ZK. So this was, remember, this was just the number, so k is a positive integer, and zk was just the number, so 0 to 1. And here we just send a number n, so what we call R of n, so the rest that we get divided by k. And here we had defined an addition, which was just by taking the rest of the sum. And so by definition, this map is a homomorphism. So this is a homomorphism. So there are some simple marks. So if I have a group homomorphism, F is group homomorphism, then it follows that F of the neutral element is the neutral element. So the neutral element in G is the neutral element of H. And for any element, F of the inverse element is the inverse of F of A. This is a straightforward calculation. For instance, for the first one, 1, I can for instance write 1 times F of 1 on H. This is as 1 is a neutral element, just F of 1. Same of F of 1 times 1 equals to F of 1 times F of 1 because it's the homomorphism. And now I can cancel the F of 1. And so I get F of 1. Okay, so this is just a straightforward application of first section is group theory, and in the same way, also the second one is f of 1. This is 1, and I can write this a times a to the minus 1, which is f of a. F of a to the minus 1. So this is f of a and then f of a to the minus 1 by inverse. Okay. Also some other things are here, for instance, the composition of group homomorphisms. Group homomorphism F H G H Again, my check is obviously straightforward, and on the other hand, so there's two. First, slightly more interesting thing with the group homomorphism, we have two somehow groups associated to it. One is the image and one is the kernel. So, definition. F H, the group homomorphism the kernel is the inverse image of the neutral element is the kernel of F, which is the set of all the images such that F of A 1. So any and the image can write it as image of F, which is the same F of G, so this is the set of F of A in G. So this is subset of H, and this is a subset of G. And then the result, I mean the remark, which I just get from proposition. So both the image and the kernel are subgroups. The kernel is a subgroup of G, and the image is a subgroup of H. But the kernel is something better. It is a normal subgroup. So image F is a subgroup of H, and the kernel of F is a normal subgroup. In fact, we see in a moment that in some sense also the converse is true. For every normal subgroup, there is a homomorphism. So for every normal subgroup of G, there will be a homomorphism from G somewhere, such that its kernel is precisely that normal subgroup. But anyway, so maybe I will not check. It's straightforward to check that the image is a subgroup and that the kernel is a subgroup. So maybe I don't check this again. So easy to see. Everything is easy to see, but quite a bit easy that the image of F is a subgroup. And the kernel. Just want to see why the kernel of F is somehow better. That it's even a normal subgroup. That's also for a very simple reason. So let now H in element of the kernel of F and A in element in G. And if I take F of A to the so A to the -1 HA, I have to show that this is also in the kernel of F to show it's a normal subgroup. Well, but that's here because this is F of A to the -1 F of H. F of H is 1, and so you can forget it. So this is F of A to the -1, which I can write like this.
ये तो थोड़ा बंगाली सा या पाकिस्तानी इंडियन सा अलग लग रहा है।
डंकी लगा गया है मुझे लगता है।
हाँ?
डंकी लगा गया है जहाँ पे गया है। डंकी संगीत है ना कुछ रास्ते थे।
Question, or is there some, or has somebody decided to not forgot to turn off the microphone? Apparently there's no question. Okay, and so thus it follows that turn F's normal subgroup. Okay. So now just a few more words because that's always part of the story at the beginning of the words. So we call so an isomorphism H is projected and so we need an isomorphism from itself called an automorphism. Actually, it's an automorphism. Automorphism. And it's clear that if F and VTH is an isomorphism, then it follows immediately that F to the -1 VTH is also a homomorphism, and well, obviously from H to T also an isomorphism. Check that it must be a homomorphism. So then, normally when you call something an isomorphism, it has an inverse. That is therefore good. Okay. And in this case, so if there is an isomorphism and the S isomorphic. H. And it's clear that being isomorphic is an equivalency. Yeah, it's an exercise. So the first, so one thing is, so we have something similar to linear algebra. In linear algebra, you also have the notion of the kernel, and you know that the linear map is injective if the kernel is 0, and this is also the case here. And it's also a very simple fact. Mark. Groupomorphism. F equals to H is injective. In the kernel of F. Only consists of the neutral element. This direction is essentially trivial because we know that 1 always lies in the kernel because 1 has to be set to 1, and if the map is injective, then every other element will be sent to something else, otherwise it would not be injective. Yeah. And now let's look at this direction. It's not much more difficult, so we soon. One, and that assume we have two elements A, B, which have the same element. Well, so then it follows that if I say A to the minus 1 B, this is F of A to the minus 1 B, and this is equal to 1. So that means E to the minus 1 is an element of the kernel of F, which is 1. So follows that A to the minus 1 B 1. By A, so that these. Okay, so this is quite simple. Let's run more an example, which I call exercise. Okay, important. So that F, M, and the projection of sets the two projective sets, then their groups of permutations are isomorphic. For instance, I can say take this map, which I call star, from the group of permutations M, so all the projections from M to itself, so all the projections N to itself, which just sends such a projection. So the following, the first, so we have we want to find a projection of N to itself, so we take the inverse of F, so go to M, then you apply an element here, and then you make go to sigma maps to F composed with sigma composed with F to the minus. Okay, so we have want to map from N to itself. So first we map N to M by the projection, then we apply this permutation, and then we map the factor. And this is an isomer. You can easily see. I mean, this is an exercise. So there's nothing deep going on. It looks like more complicated. It is straightforward. Just have to see what happens. Also not particularly. Okay. So in particular, we have this. I had noted Sn. So if M has an element, then therefore we have that this set of permutations of M is just isomorphic to Sn, which we actually call, which was just the permutations of the set 1. Okay, this was just an example. Now, maybe a more important example for homomorphism one always has is that if you have a group and a normal subgroup, you can map every element in the group to the corresponding coset. And this is a group homomorphism. So, lemma selection of the group. And normal subgroup. And then for next projection phi on G, so G n, which sends an element A, so the coset AN is a group homomorphism. In fact, it is a subjective group homomorphism. With kernel F. Okay. In particular, we see that indeed normal subgroups are precisely the kernels of the group homomorphism. And what of course P is simply called canonical projection. So, okay, there's not much to show. So by definition, we have so P of A is just phi of A is just An. If I take the full element phi of A times phi of B equals so An times Bn, we know that the group structure is that this is An and this is phi of A. Okay, so that's nothing to show. So this is a group homomorphism. And what is kernel? So if A is an element in the kernel of P, this is equivalent to A being sent to the neutral element here, which is 1 times n equals to n. And this is equivalent to A itself being an element in n. So thus, kernel is in. And the map is subjective by definition, because obviously every coset is a coset of some element. Okay. So maybe just that we don't really use it, but I introduce this with another word. So if we have a group and a normal subgroup, then we can, we can take the factor group or the quotient group by this group, and so we can somehow describe the group in some way in terms of two simpler groups. The factor group and the normal subgroup by which we divide. So, somehow you could take these as kind of pieces from which you kind of somehow, obviously one doesn't know how it fits together, but these are the building blocks of the bigger group. And so we call it group simpler if you cannot simplify it simple, if you cannot simplify it more in this way. So there's no normal subgroup. So definition. Simple. And well, obviously no normal subgroup cannot be, because you know that 1 is a normal subgroup, also 2 is not subgroup. It's normal subgroups. Just G and subgroup consisting of the element. So we have seen in this specificated, but as an example, if the order of G is a prime number, then G is simple. But we had seen that take any element in the group which is not the neutral element, then it generates the whole group. So there can be, it actually contains no subgroup except for one entity. So that is all normal. And we also have seen that S3 that the group with 3 elements is not simple. Okay. There was some huge project, and I think mostly when I was a student, to classify all finite simple groups, which was then finished after a lot of work. I think people are still checking whether it's actually true, and there is some kind of, there's so and so many families up to isomorphism of finite simple groups, and so many isolated examples. And I think the proof is a few thousand pages, so it's like that. And, yeah, I don't know precisely. Anyway, so this is something that people have tried to figure out what are all the building blocks of the finite groups, and this can be actually answered. But the answer is very complicated. Okay. So there is so in some sense we want to have some kind of converse of this, namely you see that if we have a normal subgroup group, we get a surjective homomorphism to this quotient group. Now you could also ask yourself, assume you have a surjective homomorphism. Or anyway, so what I want to claim is if you have a surjective morphism from one group to another, then the target is actually isomorphic to the quotient of the group you start with by the kernel. So you can always, when one says this, you can always factor this homomorphism by the kernel. So let me just take it. I call this the homomorphism theorem. I think that some people call it. There are different terminologies, but this is how I like it. Homomorphism theorem. So that P in MTH projected homomorphism which say maybe like this name with kernel K, then there is obviously can divide G by the kernel, which is according to what we know normal subgroup, and then we get morphism from this quotient to H, and this actually is an isomorphism. And then this follows there exists an isomorphism. So which of course bar from G to H, and I can also say such that in suitable sense map phi factors to this, so which I can say that phi can be written as the bar composed with pi. So obviously pi is the map from G to G of K is the net projection. Which is one point. Write this as a diagram of G of H, our morphism. You can go here by a pi, G of K, and then this pi bar. Let's take the diagram to mix. So the statement takes a bit longer to write down the proof because it's in some sense obvious. So we have made here some condition. We wanted pi bar composed with pi is equal to pi. So what does that mean? So the condition pi is equal to pi bar composed with pi says that for all G, A and G, if we take pi bar of AA, this is equal to pi of A. That's what it says. And so we can use this as a definition of pi bar. You only have to make sure that the definition makes sense. So use this as definition. So So in particular, I could have said there exists a unique isomorphism if I had wanted to. Okay. Uses that definition, so that means we define phi bar of AK to be phi A for all A in G. Now, obviously, we have to see that this definition makes sense, so that this is well defined. Actually, you can at the same time show that it's well defined and injected. So, phi bar is well defined and injected. What's that? So then two things have the same image, AK is equal to BK. So for AK is equivalent to saying that if I multiply, say, by A to the minus 1, A to the minus 1 B is in K. Which, remember, is the kernel of P. That means if I apply P, so equivalent to P equal to 1 P is equal to 1, this is equivalent to P of A is equal to P of P. And so if we have elements by the same coset, they are mapped. This is if and only if they are mapped to the same thing. And so this map is both well defined and injected. And obviously, P bar is surjective by definition. Because the original map P was supposed to be surjective, and we have defined P of AK to be P of A. So A is an arbitrary element of G. So every P of A occurs in the image by definition. Okay. And so, okay, it's not quite so. We still have to see. We still want to see that this is a homomorphism, but that's. So I take P bar of AK and BK. So according to the definition is P bar of AK, which is equal to P of AB. Which according to our definition is equal to bar of AK. Okay. So this is just the definition. Correct. Okay. So just one. Yeah, so this is one little example. Example that already several times for other things. So that K is equal to integer. We have this map R from Z to ZK, which sends the number n to R of n, which is the rest under division by K, and this we know is a surjective two-component. And what is its kernel? The kernel consists of all integers, so that the rest, if I divide by k, is 0. So all numbers divided by k. So its kernel k times. And so thus we have, if I take the quotient z modulo the normal subgroup kz, this is isomorphic to z. But it's a very briefly introduce another subgroup, which one often encounters, which is the center of the group. Not too much with it, but we have in future division. So the center of G is the set of all elements in the group which commute with all others. So if you multiply them, okay. So center of G. Right. This is Z. C of G is set for G, such that A B is equal to A for all the okay, so all the elements which commute with all of them. So G is a normal subgroup. Namely, if A is in the center of G, is an element in G, then so we call G in G, then G A G to the minus 1 as A commutes with G is the same as A G G to the minus 1 A. So in particular, it's in the center. But you know, it's much more. So that's just this is the normal subgroup. Then you can also see, in particular, we see that G is abelian. Any two elements commute if and only center. Okay. Well, as much as I wanted to say about this part. Are there any questions? So now I want to start with the next chapter, which is for the next thing, which is a group about group operations. We're not very far, but I want to start. So, in some sense, that at the beginning of group theory, that's how everybody always talks about group theory. The idea was always, and to some extent still is, that groups are about symmetries. So you have some for instance, so that means symmetry would mean you have some object and you can move it around in certain ways without changing its shape. And these are the symmetries. For instance, if you have a square, then the symmetries would be the rotations, the reflections along the sides, and so on. And these kind of bring it to itself. And you will see that these operations that you can do form a group. And so, so operation means that you have a set, and every element in the group will move the elements in the set around in such a way that this is compatible with the structure of the group. And so let me find this. So let's see the group. The X is set. An operation action of G and X is a map. I just note it again as a multiplication, although it's different from multiplication 2, from G times X to X, which sends element G and G, one X and X, so the action of G and X, such that just two actions hold. First, the identity element 1 in G shouldn't do anything. Every element is sent to itself. So 1 times X equals to X for all X in X. So identity X2. And the second one, a very simple property, is that this action should be compatible with the multiplication in the group. So if I take two elements in the group, A and B, and I let them act on element X, this is the same as if I let them act one after the other. A times B. So this is action. So this is for obviously for all A, B, and G, and all action is compatible with multiplication. Very simple condition. For instance, very trivial. Because if you take the symmetric group in n letters, it acts on the set of number 1 to n by just doing what it's supposed to do, being a projection from the set itself. So, example. So again, Sm acts on S1 n by, if I have an element sigma here, how does it act on a number I between 1 and n? Sigma by itself is a bijection from 1n, from set 1 to n to itself. So sigma times I, the operation, is defined to be sigma of I. And clearly, if I take the neutral element here, which is the identity, it sends every I to itself. And if I take the sigma composed, so multiplication here is the composition times composed with tau of I, which is sigma of tau of I, which according to our definition is sigma times tau. simple example of an action. Then another one which we will what is number 3? So the second one is a very simple. So now I want to introduce two operations of the group on itself. One of them is just by multiplying elements, which is called left translation, so the GB group. So multiplication in G defines action, or defines an operation, which are called L, from G times G, G, which says how do I act with an element of G on another element of G by multiplying. So it's just GH. G times H, but this is the product in the group. And this is called the left translation. And another action which one encounters often, and it's clear because the multiplication group is associative, that this is an action. In the same way, again, G group, we have the action by conjugation. So we have the map G times G to G, and the element G and G acts on an element H and H by sending H to G, H, G to the -1. This is the multiplication action. This is also an action. So this is an action. And because operations, whatever, because we have two elements. And also H and G. What does it mean? So if I first apply B to H, I get B, H, B to the -1. No, let me just say. So if I, for instance, if I apply AB, H, AB to the -1, what this is the same as A, and then here B, H, B to the -1, A to the -1. Because the inverse doesn't get around, I can do it like this. So we can see we have the action on H by AB is the same as first acting by B, and then by A. But yeah. So this is also 5 minutes. Sensible. Yeah. So what I'm now aiming for is getting our second theorem, which is Haley's theorem, that every finite group is an isomorphic closed subgroup of a symmetric group. But we won't quite get there. Operations. So the first remark is that if we have such an action, then just applying one, acting with one element on all the elements in the set we're acting on gives a bijection of the set to itself. So definition. So let's G X on the set X. So I now just say multiplication. This depends on the action that we're given here. Multiplication. By element G and G, and is the map say MG from X extends X to G times X. Okay. So for every element G and G, we have a map from X to X. And by definition of an action, we have that M of the neutral element, one of the group, is equal to the identity. And now I claim that these are all these MG are all projections. So note for all GMG, if we take MG, say MG to the minus 1, we take the inverse element, we compose the map given by with that by G, and we apply it to X. What is that? Well, by definition, it's not something quite as complicated. It is just G times X times G to the minus 1. And now, of course, this is an action. This is the same as G to the minus 1 times G. Now, the multiplication group. X, this is 1, and so this is equal to X. And so, and the same in the same way. We have MG composed with MG to the minus 1. So this means this composition, MG to the minus 1 times MG, is the identity of X. And in the same way, this is also the identity. And so we see that these two maps are inverse to each other. So that's MG and MG to the minus 1 are inverse projections. In particular, all these MGs are projections. Then maybe I can stop. Or lemma. So that means if we have such a group action, then this map MG, which is just multiplying with G with the action, is a projection of X to itself. So if you wish, it's an element in the symmetric group on X. So we therefore have a map from the group G to the symmetric group on X, and that creates the group homomorphism. So that G, the group G, X, we have the corresponding multiplication, then the map M from G. So the group of projections X itself. Constant sigma X sigma projected is true. So, and what is this? What is this map? I haven't said it. So I sent G. So this map and okay. So this is very simple. So we take G and H. G X. So what do we have to show? We have to show that the product in G corresponds to the composition in symmetrical. And if I take M of GH, product of H of X, this is G times H GH, so the product GH acting on X, but according to the by definition and according to the fact that it's an action, this is just H times X and G to it, and this is MG composed with MH. Apply to X, and the product is the composition. So this is a group. Okay, so that's all I wanted to say today. Next, we will use this fact to show that every group is a subgroup of symmetric group by just finding a suitable action of G on itself, so that G will be that the corresponding map here M will be injective, and then G becomes a subgroup of the corresponding symmetric group on G. Okay, we'll see you next time. Are there questions?
Oh, yes. How can we collect our solution for the exercises?
What?
Where should we scan the solution for the exercises?
Well, I haven't yet, these, when I write exercise here, these are not, this is not homework. It just means if it's not obvious to you, you can. But I will this weekend give you exercises, and you can, I don't know, you could put it in my email or something. I have a mailbox, if you know, in my thing. Otherwise, you can also send it to me by email if you want to scan it. But as you are allowed to run around, I think you could. Maybe you can ask somebody where this, in the math corridor, there is a mailboxes. I have a mailbox with my name, and you can put it there. But I haven't yet, I will over the weekend, Monday or so, send you homework, and then you can do it. But these things, when I write exercise, these are always very simple things, and you just, you're supposed to check whether you also find them simple or not. And so that means if they're not obvious to you, you can check them for yourself. That's all I mean there when I say exercise. Okay.
Okay, thank you.
Okay, so thanks. So then I will stop. Okay. Bye-bye. So this is thinking. For some reason, they have this terrible chalk which one can't actually write. So I always bring my own, but today I didn't bring enough. So, so it has this property that
It breaks a lot.
so it has very strong resistance, so you have to lose a lot of strength.
Yeah.
It breaks very easily, and once you have written it, it's very difficult to get off the blackboard. So there's all.
Also, that eraser is not very good.
That's true, but with good chalk you can use it. But this is, just it has all possible negative properties, but I think it's a bit cheaper than the normal. Okay, so goodbye. I don't know why this is.
Thank you, Professor.